Everything that exists survives by spinning. Planets, stars, and galaxies do not rotate by accident. They rotate because without spin, gravity would collapse matter before structure could ever form. Spin is not a visual detail of the universe. It is a physical requirement for stability. Without angular momentum, planets could not regulate temperature, stars would burn out or implode, and galaxies would tear themselves apart. Right now, the Earth is rotating beneath you at over 1,000 kilometers per hour. It orbits the Sun at more than 100,000, and the entire solar system moves through the Milky Way at hundreds of kilometers per second. Yet none of this feels real. Everything feels perfectly still. Why does the most important motion in the universe escape your senses? And what does that blindness hide about how reality actually works? In 1632, Galileo Galilei proposed a thought experiment that defined the nature of our perception. He asked us to imagine being inside the cabin of a ship moving steadily across a perfectly calm sea. With no windows to view the horizon and the vessel moving at a constant speed, there is no physical experiment you could perform to prove you were moving. Drop a ball, and it falls straight down. Jump, and you land in the same spot. This is the principle of the inertial reference frame. Physics behaves the same, whether you are standing still or moving at a constant velocity. Your brain has evolved to exploit this principle. It is wired to detect acceleration changes in speed, not velocity itself. Right now, your vestibular system reports that you are stationary. This is the biological blind spot. To see the reality of your position, we must strip away the illusion of the closed cabin and examine the physical motion of the Earth directly. If we shift our reference frame from the chair you are sitting on to the center of the Earth, the stillness vanishes immediately. At the equator, the planet is rotating at approximately 1,670 kilometers per hour, faster than the speed of sound. You are moving with the Earth at supersonic speed held in place by gravity, but the Earth is not a fixed point spinning in a void. It is racing around the Sun. Shift the frame again to the solar system, and our velocity jumps to nearly 107,000 kilometers per hour. We are covering 30 kilometers every second following a broad, nearly elliptical path through space. Yet even the Sun is not a stationary anchor. It is dragging the entire solar system through the Milky Way at a staggering 828,000 kilometers per hour. And if we seek the ultimate frame of reference, the cosmic microwave background, the primordial light left over from the early universe, we find that our entire local group of galaxies is hurtling at 368 kilometers per second toward a gravitational anomaly in the constellation Leo. We are not sitting still. We are participating in a dizzying choreography of vectors spinning while orbiting, while drifting all superimposed into a single complex trajectory through spacetime. The only reason this violence does not tear the surface of our world apart is that the motion is perfectly stabilized. We are protected by a mechanism so efficient that it renders the speed imperceptible, a mechanism that relies on the very spin that propels us. The rotation of our planet is often taken for granted as merely the mechanism that provides the rhythm of day and night. But from a physics perspective, the day-night cycle is a secondary byproduct. The primary function of Earth's spin is structural stabilization. The planet acts as a massive gyroscope, and its rotation is a primary stabilizing factor, preventing large-scale climatic instability. This angular momentum is not intrinsic to the rock itself. It is a stored quantity of energy, a legacy of early solar system dynamics. Approximately 4.5 billion years ago, a Mars-sized protoplanet, often referred to as Theia, collided with the young Earth. The impact was cataclysmic, nearly pulverizing both worlds. Yet the system conserved the energy of that collision, converting the linear force of the crash into rotational velocity. The Earth absorbed the blow and began to spin wildly, essentially becoming a planetary-scale flywheel. This rapid rotation forces the planet's equator to bulge outward. Earth is about 43 kilometers wider at the waist than from pole to pole. This distortion is crucial. The equatorial bulge acts as a counterweight, anchoring the planet's axis against the gravitational tugs of Jupiter and the Sun. Without this gyroscopic stabilization, Earth's axial tilt, currently holding steady at 23.5 degrees, would wander erratically over geological timescales. We can see the consequences of losing this stability by looking at Mars. Lacking a massive stabilizing moon and possessing a less pronounced equatorial bulge relative to its external perturbers, the red planet's axis has swung wildly in its past, triggering extreme climate shifts that likely stripped it of its habitability. Furthermore, spin acts as a thermal regulator. By rotating every 24 hours, the Earth ensures that solar energy is distributed evenly. If the rotation were significantly slower, the day side would bake under prolonged exposure, while the night side froze, creating atmospheric pressure gradients so violent they would scour the surface. The spin is the engine that drives the Coriolis effect, organizing these temperature differences into stable bands of wind and weather. We survive because the flywheel is still turning. However, this mechanical stability is not permanent. We are slowly dissipating rotational energy. The Earth is not spinning in isolation. It is gravitationally coupled to the Moon, and this relationship acts as a relentless drain on our rotational inertia. The mechanism driving this loss is tidal friction. As the Moon orbits, its gravity pulls on Earth's oceans, creating a tidal bulge. Because Earth rotates much faster than the Moon orbits, 24 hours versus 27 days, the planet's spin drags this water bulge slightly ahead of the Moon's position. This creates a gravitational misalignment. The forward displaced mass of water pulls the Moon forward, adding energy to its orbit, while the Moon pulls back on the water, creating drag on Earth's rotation. This is a transfer of momentum on a planetary scale. We are trading our spin for the Moon's distance. Data from the Apollo laser ranging experiments confirms that the Moon is spiraling away from us at a rate of 3.8 centimeters per year. In exchange, Earth's rotation is breaking. Our day lengthens by approximately 1.7 milliseconds every century. This may seem negligible to human perception, but over billions of years it is a definitive trend toward equilibrium. The ultimate endpoint of this process is tidal locking, a state where the Earth's rotation slows to match the Moon's orbital period exactly. At that theoretical point, the transfer of energy would cease, and one side of Earth would face the Moon eternally. This planetary flywheel is slowly winding down its energy dissipated into the heat of moving oceans and the expansion of the lunar orbit. Yet if a single planet can be drained of its momentum by a small moon, what happens when an entire solar system is subjected to the gravitational turbulence of a galaxy? If we zoom out from the local mechanics of the Earth-Moon system to the scale of the Milky Way, the picture of our stability changes drastically. A common misconception, often reinforced by two-dimensional textbook diagrams, is that the solar system traces a neat, closed circle around the galactic center, returning to the same point every cosmic year. This is a simplification born of a simplification imposed by a convenient reference frame. In reality, our trajectory is far more volatile. The solar system is moving at approximately 230 kilometers per second relative to the galactic center. Because the planets orbit the Sun on a single orbital plane, known as the ecliptic, and because that plane is significantly inclined relative to the Sun's motion through the galaxy, we are not sliding through space like a plate. We are moving through it along a helical path. The planets trace a helical path spiraling around the Sun as it races forward. While viral animations often exaggerate this into a vortex trailing behind a rocket-like Sun, the core vector geometry holds true. We are corkscrewing through interstellar space. Furthermore, the Sun's orbit itself is not a simple ellipse. In the solar system, 99.8% of the mass is concentrated in the Sun, creating closed, predictable orbits for the planets. But the Milky Way has no single point of mass. The gravity governing us comes from a diffuse soup of stars' gas and the vast invisible halo of dark matter. Because this mass is spread out, the Sun does not return to its starting point. Instead, it traces a rosette pattern, an unclosed flower-like epicycle that precesses over time. We are not circling a track. We are moving through a diffuse gravitational field subject to currents we are only just beginning to map. The complexity of our path introduces a massive periodic variable into the equation of survival vertical oscillation. We do not stay fixed on the galactic plane. The Sun oscillates vertically through the galactic disk. This oscillation is driven by a gravitational restoring force. As the Sun drifts upward away from the dense concentration of stars in the galactic disk, the collective gravity of that disk pulls it back down. We overshoot the mid-plane, sink to the bottom, and are pulled back up again. Data from the Gaia Space Observatory indicates that this cycle repeats roughly every 60 to 64 million years, with an amplitude carrying us about 100 light-years above and below the center line. This motion is significant because the galactic disk is not empty space. It constitutes a region of elevated interaction risk. The midplane is the region of highest stellar density, filled with massive gas clouds and potential supernovae progenitors. Traversing this zone is a statistical hazard. When the solar system passes through the crowded galactic midplane, the gravitational influence of passing stars and molecular clouds increases. These perturbations can destabilize the Oort Cloud, the vast shell of icy debris surrounding our solar system. A nudge from a passing star can send a shower of comets hurtling inward toward the inner planets. It is a controversial but compelling theory known as the Shiva hypothesis that these galactic crossings correlate with periodic mass extinctions on Earth, including the KPG event that ended the reign of the dinosaurs. We are essentially playing a game of orbital roulette every 60 million years. Currently, we are located a few dozen light-years above the midplane, slowly climbing out of the danger zone. In this region, spin is a matter of orbital mechanics, material bodies moving through relatively flat space. But there are regions in the universe where rotation ceases to be about movement through space and becomes the dominant force shaping space itself. In our journey through the solar system and the galaxy, we have treated spin as a property of matter planets rotating and stars moving through space. In these environments, space itself is a passive stage, a fixed background against which motion occurs. But there are regions in the universe where the density of matter becomes so extreme that this distinction collapses. Here, rotation ceases to be merely a movement through space and becomes a mechanism that churns the fabric of reality itself. When a massive star dies and collapses into a black hole, it does not lose its angular momentum. The conservation laws compel the collapsing core to spin faster and faster as it shrinks. The result is a Kerr black hole, a rotating singularity. Unlike the static spherical Schwarzschild black holes, often depicted in early theory, a Kerr black hole is a dynamic engine of geometric distortion. According to Albert Einstein's general relativity, a rotating mass drags the surrounding spacetime along with it, an effect known as the lens-thirring effect, or frame dragging. To visualize this, we must discard the idea of space as a vacuum and view it through the lens of fluid dynamics. Imagine the black hole not as a solid ball, but as a rapidly rotating object embedded in a medium that resists differential motion. As the turbine spins, the fluid closest to it is dragged into motion due to friction. Around a rotating black hole, spacetime behaves analogously, as if it resists being left behind. The black hole grabs the coordinate grid of the universe and twists it into a spiral. If you were to hover near such an object and release a beacon, the beacon would not fall straight down. It would instantly begin to orbit the black hole, not because any force is pushing it sideways, but because the space it occupies is flowing sideways. The straight line, the geodesic, has been bent into a helix. This is not theoretical speculation. The Event Horizon Telescope captured the first historic image of the supermassive black hole at the center of the galaxy, Messier 87. The data from that observation is consistent with a rapidly rotating object. The polarization of light around the shadow suggests a magnetic field twisted by the intense rotation of the black hole, which is estimated to be spinning at more than 90% of the maximum rate allowed by physics. In this regime, the geometric riptide is so powerful that it overwhelms all other forces. As we descend closer to the event horizon of a Kerr black hole, we cross an invisible boundary known as the stationary limit surface. Beyond this point, we enter the ergosphere. The ergosphere is a region of overwhelming physical constraint. In this zone, spacetime itself is dragged around the black hole faster than light can travel through space. In standard physics, nothing can travel faster than light through space. However, relativity allows space itself to flow at any speed. Inside the ergosphere, the fabric of the universe is dragging you along the black hole's rotation faster than a photon can fly against it. This leads to a fundamental physical constraint inside the ergosphere. Standing still is a physical impossibility. To remain stationary with respect to the distant stars, you would need to move against the flow of space faster than light, which is forbidden. No amount of engine thrust, no amount of energy can hold you in place. You are forced to rotate. The future of every particle in this zone points inevitably in the direction of the spin. You can still escape the black hole you haven't crossed the event horizon yet, but you cannot avoid co-rotating with it. This forced rotation contains immense energy. Because the twisting of space is a form of kinetic energy, it is theoretically possible to extract it. This is the Penrose process. If an object were to fly into the ergosphere and split in two, dropping one half into the black hole while the other kicks backward against the rotation, the escaping piece could steal some of the black hole's angular momentum. It would exit the ergosphere with more energy than it entered, effectively mining the spin of the singularity. Nature likely performs this process automatically. The colossal relativistic jets seen shooting out of quasars and active galactic nuclei are believed to be powered by this mechanism. Magnetic fields threading the ergosphere, twisting up like tight rubber bands until they snap, launching plasma into the void at near light speeds. These jets are the exhaust fumes of the universe's most efficient engines, powered entirely by the geometry of spin. This reveals a profound truth: rotation is not just movement. It is a fundamental reservoir of energy capable of twisting the laws of causality and powering structures across millions of light years. But if spin is this dominant, if it is the default state of everything, from the smallest asteroid to the largest singularity, it raises a fundamental cosmological question: where did this angular momentum originate? If we view the universe as a closed system, the ubiquity of rotation presents a physics puzzle. According to the conservation of angular momentum, the net angular momentum of the universe is expected to be close to zero on large scales. If the Big Bang was a perfectly symmetrical expansion, every clockwise rotation should be canceled out by a counterclockwise one. Yet wherever we look, from the disks of galaxies to the accretion flow of black holes, we see organized, coherent rotation. This implies that the current state of motion is a fossil record of the universe's initial conditions. To find the origin of this motion, we must look at the first kick. It did not come from a mechanical push, but from the inherent uncertainty of quantum mechanics. In the first fraction of a second, the universe was a subatomic soup ruled by quantum fluctuations, tiny random jittering of energy density. When the phase of cosmic inflation occurred, space expanded faster than light, stretching these microscopic quantum jitters into macroscopic scales. The universe that emerged from this era was not perfectly smooth. It was textured. Some regions were slightly denser than others. As gravity began to collapse these overdense regions into the first structures, the matter did not fall inward in straight lines. It was subjected to tidal torques, gravitational tugs from neighboring clumps of matter. Just as an uneven floor causes a rolling ball to curve, the uneven distribution of mass in the early universe caused the collapsing gas clouds to twist. This is the origin of large-scale cosmic rotation. The spin of the Milky Way, the rotation of the Sun, and the turning of the Earth are all magnified echoes of the quantum noise that existed 13.8 billion years ago. We are spinning today because the Big Bang was not a perfect explosion. It contained intrinsic fluctuations and asymmetries. The imperfection of the beginning is what allowed structure to emerge. Perfect symmetry would have resulted in stillness, and stillness would have meant a universe without galaxies. But the universe did not just imprint motion onto stars and galaxies. It appears to have encoded a specific directionality into the chemistry of life itself. This is the mystery of chirality, or handedness. In a laboratory, if you synthesize amino acids, the building blocks of protein, you get a 50-50 mixture of left-handed and right-handed molecules. They are chemically identical mirror images. However, life on Earth is strictly asymmetric. The amino acids in your body are almost exclusively left-handed, while the DNA helix spirals to the right. This homochirality represents a strong statistical bias. Why did life choose the left path? The evidence points back to astrophysical processes. In 1969, the Murchison meteorite fell in Australia. Chemical analysis revealed that this ancient rock, older than the Earth itself, contained an excess of L-amino acids, the left-handed form used by life on Earth. This suggests that the bias existed in the solar nebula before life even began. The selection was not made by biology but by astrophysics. The leading hypothesis points to circularly polarized light in the star-forming regions where our solar system was born. High-energy radiation from massive stars scattered by dust grains can spiral in a specific direction. This spiraling light acts as a chiral filter, destroying right-handed molecules in the dust cloud while leaving the left-handed ones intact. When the Earth formed from this dust, it was already seeded with a chemical bias. We are not random accidents of chemistry. We are the downstream result of a cosmic asymmetry. The spin of the radiation field in the nebula determined the molecular geometry of every living thing on this planet. We carry the handwriting of the universe in our genetic code, a permanent record that physical processes can encode directional asymmetries. Spin is not just how we move, it is quite literally how we are built. In our human experience, the rotation of the heavens seems eternal. The sun rises, the stars turn, and the galaxy spins with a constancy that suggests permanence. But in thermodynamics, there is no such thing as a perpetual motion machine. Spin is simply a reservoir of kinetic energy, and like all energy, it is destined to dissipate. The universe is slowly redistributing and dissipating rotational energy. On the planetary scale, we have seen how tidal friction drains the spin of worlds, locking moons to planets and planets to stars. But even in sparsely populated regions of space isolated from tidal forces, rotation is not safe. The mechanism of decay here is subtler but more profound: gravitational waves. As predicted by Einstein and confirmed by the LIGO Observatory, any massive object that spins or orbits asymmetrically disturbs the fabric of spacetime, sending out ripples that travel at the speed of light. These waves carry energy away from the source. The binary pulsars observed by astronomers are slowly spiraling inward as they shed their orbital energy into the void. Even the mighty black holes, after they merge, undergo a ring-down phase, shuddering like a struck bell to shed their excess distortion before settling into a quiet state. This is the long decay. We are witnessing a gradual long-term dissipative process. The universe is evolving toward lower energy configurations. Over trillions of years, orbits will decay, large-scale structures will gradually relax and disperse, and the great cosmic flywheels will finally come to a halt. This leads us to the final verdict on our existence. The history of the universe is essentially a long-term competition between opposing physical tendencies: gravity, which drives matter toward increasingly compact states, and angular momentum, which fights to keep it apart. Spin is the resistance. It is the delaying action that prevents the cosmos from collapsing instantly into a singularity. It creates the structure of the atom, the orbit of the planet, and the disk of the galaxy. It allows stable structures to persist against gravitational collapse. But thermodynamics dictates that entropy must increase. The ultimate destiny of the universe is heat death, a state of maximum equilibrium, where all gradients are smoothed out, all temperature differences vanish, and all motion ceases. We are moving toward a future approaching thermodynamic equilibrium. However, that is a story for a time far beyond human comprehension. Right now, we are the fortunate beneficiaries of the era of motion. We live in the brief, brilliant window where the universal centrifuge is spinning at full power, generating the energy, the climate, and the stability necessary for consciousness to observe it. We are not merely passengers on a rock. We are the observers of a temporary but remarkable deviation from equilibrium.